Welcome to a series of videos I've prepared on the topic of tensor calculus. My name is Jim Fowler. Over the years, I've come to recognize tensor calculus as one of the more interesting and fulfilling branches of mathematics. My goal here is to share what I've learned in hopes that others may gain a similar appreciation. What I want to do in this first video is to answer the question, why tensor calculus? Before we jump into the development of equations and syntax rules, it behooves us to answer a few basic questions. What is tensor calculus? What does it do for us? What are its benefits? Hopefully this video will go a long way toward answering those questions and provide some motivation going forward. Let's start with the definition. In mathematics, tensor calculus or tensor analysis is an extension of vector calculus to tensor fields. Contrasted with infinitesimal calculus, tensor calculus allows presentation of physics equations in a form that is independent of the choice of coordinates on the manifold. This is a quite reasonable definition, but if you're new to tensor calculus, I'm not sure it helps much. After all, you probably see some terms that are new to you here, such as tensor, tensor field, and manifold. We'll define and discuss these terms in due course, but right now I want to focus on this second statement. The one that says tensor calculus allows presentation of physics equations in a form that is independent of the choice of coordinates. This is the real strength of tensor calculus, and it's what we want to talk about today. Science has always relied heavily on math. In fact, I'm not sure we could make headway at all were it not for mathematics. As I see it, the main goal of science is to establish mathematical models for cause and effect relationships that we observe in the world around us. And more often than not, these relationships involve such things as points, lines, surfaces, area, volume, and so forth. Thus, if we really want to understand physical phenomena, we must have a thorough understanding of geometric principles, and that means we also need a robust set of mathematical tools to work with, and that's exactly where tensor calculus comes in. My first year of high school math many decades ago was devoted to basic algebra. The second year was Euclidean geometry, where we worked directly with geometric objects such as lines, angles, triangles, circles, and so forth. As I look back today, I'm amazed to see how much could be discovered this way. That is, without the benefit of a coordinate system. Let me quickly share with you my favorite example. Start with any right triangle. We'll copy it and put it on its side like this, and again here and here. And what I've done is to construct a square whose side is equal to c, and of course the area of this figure is equal to c squared. Now we'll copy the figure over here. This time I'll move the blue triangle over this way, and the green triangle over this way. And when I do, it's obvious that the same area can be represented now as the sum of areas of two squares, one of side A and one of side B. And we have therefore proven the Pythagorean theorem just by moving a couple of triangles around on the figure. Well, there are many similar examples, but in the end there's only so much you can do at this level. Real advancement occurs when we introduce a coordinate system, thus merging algebra and geometry into what we call analytic geometry. Let's look at some of the examples of what we can do with a coordinate system. Here, assigning coordinates to the endpoints of a line segment lets us determine the midpoint and length with simple formulas. Here's the formula for the midpoint, and here's what we do to find the length of the line segment. Another formula gives us the area of a polygon simply by plugging in the coordinates of each vertex. Multiply the first x value times the second y value, and subtract the product of the second x value times the first y value. Continue this pattern for each pair of vertices around the polygon, and then it's just a matter of doing the arithmetic to find out that the area in this case is 34 square units. We can also generate curves with simple equations. In this case, all of the points x, y that satisfy the quadratic equation at the bottom of the screen map out a hyperbola. We can do the same thing in 3 dimensions. Here, all the points x, y, and z that satisfy the equation at the bottom map out a surface area known as an ellipsoid. Another useful technique is to parameterize the coordinates. Here I've defined x, y, and z as functions of t. Then as we vary t from 0 to 5, the point sweeps out a curve known as a spiral. Where vectors are concerned, we know that adding vectors graphically is a matter of connecting the tail of one to the head of another, giving us what we call a resultant. For example, here we can take vector b, connect it to the end of vector a like this, and that will give us the resultant of c. But with a coordinate system, what we can do is to decompose our vector into its various components. We take vector a, decompose it into its x component, its y component. We do the same thing with b, and then to find the resultant, it's just a simple matter of addition. We add the two x components here to get the x component of the resultant. We add the y components, and that will give us the y component of the resultant. Now let's consider some operations related to differential calculus and vector analysis. Note that we can express them as you see here. In fact, when I first learned them, I believed that these were the actual definitions, but that's not really the case. This is just how they're expressed using Cartesian coordinates. If, for example, we switch to spherical polar coordinates, then the forms are quite different. Here's the gradient, the divergence, the Laplacian, and the curl. Well, they're quite different, so which form is correct? Well, they both are. It's just a matter of which coordinates you want to use. The fact is that these are functions that we call geometric objects. They are geometric in nature. What that means is that they exist as entities unto themselves as what we call invariants. We introduce coordinate systems so that we can derive quantitative results, but we'll get the same results regardless of which coordinate system we use. So coordinate systems are good and usually essential, but we have to be careful. There is a dark side. If we choose a coordinate system too early in the course of solving a problem, we often generate complex analytical expressions that obscure the geometric nature of the problem. It's often impossible to know if the resulting complexity is due to the problem we're working on or to the nature of the coordinate system itself. Most often it is the latter rather than the former. We can very easily get bogged down in ways that can be avoided if we choose the right coordinate system in the first place. And worse yet, if we choose the wrong coordinate system at the wrong time, we may never fully realize the geometric nature of the solution. Let me give you a very well-known historical example. Here you see pictures of two well-known 18th century mathematicians, Leonhard Euler and Joseph Lagrange. Among their many accomplishments was the work they did related to surfaces. Consider here the problem of minimal surfaces. Mathematically, the problem is to minimize the area integral seen here over all possible surfaces for which the contour boundary is specified. Now don't worry if the problem is over your head at this point. You'll still be able to appreciate the point shortly. In 1762, Lagrange derived and published a general solution in the form of a differential equation. And yes, that's not a misspeak. It was more than 10 years before the American Revolution. And it goes like this. If we have a surface defined as a function of x and y, then this is the differential equation that Lagrange came up with that must be satisfied in order to derive the minimal surface. Now, in this form, we're letting the subscripts represent partial differentiation, so that f sub x is equal to the partial of f with respect to x, and so on. Now, the question is, do you see any geometric significance in this solution? Well, I sure can't. And the fact is, neither did Euler nor Lagrange. To them, it was just a differential equation to be solved analytically. Well, 14 years later, this fellow, Jean-Baptiste Monnet, derived this expression for the mean curvature tensor of a surface. Now, if you compare the numerator of this expression with Lagrange's equation, it's clear that the geometric condition to be satisfied is just this one. The mean curvature must be 0. Now, the complexity of Lagrange's solution is entirely due to his choice of the Cartesian coordinate system. This amazingly simple and profound result was completely obscured for 14 years due to his arbitrary and premature choice of coordinate systems. Let me reinforce the point with another example. Consider a problem that has important applications for biological membranes, namely to find the surface S with a given contour boundary that minimizes the integral of the square of the mean curvature tensor. If we blindly apply Cartesian coordinates to the problem, we'd have to do something like this. Now, just as a forward reference, the same problem looks like this in tensor calculus. And the first term, right here, is the Laplacian operator applied to the mean curvature tensor. Okay, so if we take just this first expression and expand it out using the Cartesian coordinate system, look what we get. All right, this expression is obviously unworkable. I have no idea how anyone would go about trying to solve this. I don't even want to try. And forget trying to find any geometric significance to this thing. It's just impossible. It's a classic example of using the wrong coordinate system at the wrong time. And that leads us to a very important principle that applies to all of mathematics, and it's this. Perform all the analysis possible at the highest level of abstraction, and move to the lower levels of abstraction only when it is absolutely necessary to do so. Let me give you a simple illustration. Suppose I gave you this function and asked you to find its value for x equals pi over 5. Well, you might do something like this. You'd substitute pi over 5 for x. You'd look up the value of the cotangent to be approximately 1.376. You'd square that, add 1, take the square root, do the long division, look up the arc cosine of 0.588, and finally come out with an answer of approximately 0.942. Well, that's the correct answer, and it is, of course, what you were asked to do. But let me show you another method, and let's compare them. Again, we start with the function. This time, we'll take the cosine of both sides. And of course, the cosine of the arc cosine is just the argument itself. Now we substitute the definition of the cotangent as the cosine over the sine, multiply the numerator and denominator of the right side by the sine of x, we get this, and of course you know that sine squared plus cosine squared is 1. And then finally we apply the trigonometric identity that says that sine of x is equal to cosine of pi over 2 minus x, and since both sides are cosine functions, that means that f of x is itself simply pi over 2 minus x. Now that we've simplified it to this level, we substitute in pi over 5, and the rest of it is simply arithmetic until we come out with the same answer that we did before. All right, well, what's the advantage here? Well, several advantages. The first is we do a lot less arithmetic. You notice the only place we did any arithmetic at all is the very last step. And that means that we're not subjected to as many opportunities to make careless mistakes. And the results are probably going to be more accurate in most cases because, well, look at this example. The only place we applied any approximation at all is the very last step. Up until the answer being 3 pi over 10, the results were exact answers. It's only when we did the last division that we had to approximate a little bit. But the main reason that this is more significant is that you can see the underlying relationship in the function. We see that it's not a trigonometric relationship at all. It's simply an arithmetic relationship. F of x is just the difference between pi over 2 and x. And so we have the underlying significance of the relationship summarized in a very simple form. We totally would have missed that if we continued to use the original formula over and over again. If you look up the word calculus in Webster's dictionary, you'll find something like this. And of course, you're familiar with the specific definition as it relates to differential and integral calculus. But the term calculus has a broader meaning. Calculus is a method of computation or calculation in a special notation as of logic or symbolic logic. And tensor calculus is a method of computation or calculation that uses a simple and unique notation, expresses geometric relationships as tensor equations, and expresses them in forms that are independent of the choice of coordinate systems. All right, before I end the video, I want to introduce some of the major contributors to tensor calculus. Here we have Bernard Riemann. As a student and protege of Friedrich Gauss, Riemann went on to be recognized as one of the most gifted mathematicians of all time. Among his many accomplishments was his introduction of curved, non-Euclidean spaces known today as Riemann geometry. He was also the first to suggest using dimensions higher than 3 or 4 to describe physical reality. It was said of Riemann that he freed geometry from Euclidean prejudices. Were it not for his untimely death at the age of 39, he would undoubtedly have achieved notoriety akin to that of Newton and Einstein. This is Elwin Bruno Christoffel. Based largely on Riemann's prior work, he was the first to introduce fundamental concepts of differential geometry. This in turn opened the way for the development of tensor calculus. Next we have the Italian mathematician Gregorio Ricci Curbastro. Tensor calculus is officially his brainchild. It is he who is credited with establishing tensor calculus structure and syntax pretty much the way we use it today. Tullio Levi-Civita was one of Curbastro's students. He went on to make a number of his own significant contributions. It is noteworthy that Tullio corresponded with Albert Einstein during his development of general relativity, and on several occasions identified and corrected mathematical errors that Einstein had made prior to the work being published. Marcel Grossmann was a fellow student and a close friend of Einstein's. In the early 1900s, Einstein approached Grossmann pleading for help in formalizing his ideas of general relativity. As an expert in differential geometry, it was Grossmann who convinced Einstein that his intuitive ideas about gravity could best be described with a geometric model, and that tensor calculus was the perfect tool for its analysis. And finally, I've included Albert Einstein himself. Following Grossmann's recommendation and tutorial assistance, Einstein employed tensor calculus to formulate his field theory of general relativity. I've included him as a contributor because along the way he introduced some significant syntax simplifications. I encourage you to dig around on your own for more information on the lives and achievements of these remarkable individuals. Okay, let's talk a minute about what you might need to know in the form of prerequisites. If you're going to get anything out of these videos, you probably need to be well versed in algebra, trigonometry, and basic calculus. It would be good if you have had any experience at all with these topics: analytical geometry, vector analysis, differential equations, linear algebra, but it's not essential. But if you have had any of these things, you'll relate to the topics a little better because you'll be able to relate what we talk about here to what you already know. And then things you don't really need to know are anything about science, physics, or general relativity. This is about mathematics and not about science. Okay, I also want to introduce you to a book. This is one of my favorites by Grinfeld, Introduction to Tensor Analysis. I found it to be very easy to follow. It's very well structured, and the topics are sequenced in a very reasonable way. I'm going to tailor the videos in basically the same strategy as Grinfeld takes them in his book. Not exactly. I'll add some things and skip other topics, but basically the structure is going to be very similar. I will be using Grinfeld's syntax. So if you want something that will enhance your library a little bit, this would be a good choice. Okay, we'll wrap this up with this as the final takeaway. I found this quotation in the book, and I can't improve on it, so I'll just give it to you as is. The central idea of tensor calculus is to acknowledge the need for coordinate systems and at the same time to avoid selecting a particular coordinate system for as long as possible in the course of solving a problem. Tensor calculus provides algorithms for constructing analytical expressions that are valid in all coordinate systems simultaneously. And that in a nutshell answers the question, why tensor calculus? In the next video, we'll kick things off by reviewing the properties of Euclidean space.